Hello, this is Ken Titmus again with the fourth in the DDMRP podcast series, this time discussing demand-driven planning. To recap, in previous podcasts, we have discussed the first three of the five components of DDMRP, namely strategic inventory positioning, buffer sizing and buffer profiles, and buffer dynamic adjustment. These three components set up your demand-driven operating model, or DDOM for short, that needs to be continuously improved to increase service levels, reduce inventories, and shorten lead times. This continuous improvement process will be discussed in a future podcast. With these three components of DDMRP in place, we can start using the fourth component, which is demand-driven planning. In this section, we're going to look at some of the part planning designators and talk about the planning process for stocked parts. In the demand-driven MRP methodology, we really only teach two new unique concepts that are not already included in the traditional planning body of knowledge. The first we covered in an earlier podcast, which was the demand decoupled lead time, DLT. And the second is the planning net flow equation, which is also unique to DDMRP. Supply order generation in each of the buffers is determined by the use of the net flow equation. Net flow is calculated by taking the buffer's current on balance, adding to this any actual supply orders coming into the buffer. That could be purchased orders or manufacturing orders depending on the SKU, and then subtracting the qualified sales order demand for the buffer. Qualified sales order demand is determined by what do I need to ship today, and in the past, if I have back orders, plus any spikes I might see in demand into the future. The spike threshold is regarded as any order or combination of orders that are greater than 50% of the red zone out to a horizon of the part's lead time. So if total demand for an SKU on any particular day in the future lead time is greater than 50% of the red zone, we include the whole quantity of the spike in the equation. Of course, many of you may not see these spikes, as your customers give you an order today for delivery tomorrow. That's okay. But if you can see spikes, it does improve planning and reduce variability in the supply chain, and hence reduces the size of the buffers. So now in DDMRP planning, we're moving away from replenishing items based on inaccurate forecasts to replenishing buffers based on accurate orders or actual demand. Replenishment of the buffer happens when the quantity calculated by the net flow equation descends into the yellow zone. The rule is then to order a replenishment quantity to the top of the green zone, with a required date based on the lead time for that item. Let's try and work through an example. You might want to write these numbers down so you can get a better idea of how this works. Imagine we have a buffer with a top of yellow at 335 and the top of green at 455. For this item, we currently have 105 in stock. And when we look at the order files, we see we have 240 on a supply order. Today, we have to ship 20 on a demand order out of the buffer. So, doing the net flow calculation, it will be 105 plus 240 minus 20, which equates to 325. This number puts us below the top of the yellow at 335, and so the system would recommend a replenishment order to the top of green. So top of green at 455 minus net flow at 325 gives us a recommended order size of 130. If the net flow equation would have put us any higher than the top of the yellow at 335, there would have been no order recommendation. The net flow equation is performed on every item in your database every day. Those items that have a net flow in the yellow or red, in a worst case scenario, will have recommended replenishment orders. So not all items will be ordered every day. There are a few calculations we can perform on the buffer to provide us with some useful information. It's possible to determine the average inventory in each of the buffers. If this is then multiplied by the value of the item, it is possible to determine the average total value of the inventory in a warehouse. The average inventory in a buffer is calculated by taking the top of the red zone and adding on half of the size of the green zone. So if the top of the red zone is 100 and the size of the green zone is 60, then the average inventory in the buffer will be 100 plus 60 divided by 2, which is 130. The ideal range in which the on-hand inventory would fluctuate in a buffer is determined between top of red plus the whole of the size of the green zone. In the case of this example, that would be between 100 and 160. We can also determine the average reorder frequency and the average reorder quantity in a buffer. The average order frequency will be the size of the green zone divided by the ADU. In the example we used previously, if the green zone is 60 and the ADU is 10, this means that the buffer will be replenished on average about every 6 days. That's 60 divided by the average daily usage of 10. The average order size is generally the size of the green zone, which in this case is 60 units. At this point in the Demand-Driven Planner course, we set up a buffer and run through a 21-day simulation to see how the buffer performs. In addition, we throw in unexpected orders within the order lead time, as well as a quality hold problem with incoming material, and the buffer is resilient enough to take these problems in its stride and still maintain a 100% customer service level with no stockouts. In addition, we see the actual demand on the buffer was almost 25% higher than that for which it was built. We must not underestimate the resilience of the buffer to act as a shock absorber in the supply chain. That's basically its job. At this point in the course, we discuss the concept of decoupled materials requirements explosion. If in our bills of materials we've buffered certain manufactured components, subassemblies, or purchased parts, then the MRP generation will work slightly different, in a different way than in a traditional MRP. Although the same basic MRP algorithms, developed back in the 1960s, are still used. When a DDMRP decoupled explosion takes place, it also starts with the demand for the top-level parent item, and MRP explodes down the BOM until it reaches a buffered item, and the explosion then stops. MRP then waits until this buffered item's net flow moves into the yellow zone. The decoupled MRP will then start up again based on the replenishment quantity, and explode down to the next buffered position in the BOM and stop again, or explode to a purchased part that is not buffered, in which case the buyer would get a planned purchase order generated by the MRP system for action. The last subject we talk about in this section of the DDP course is related to distribution and what we call prioritized share. There are a few examples of this methodology we can discuss. Let's say a vendor supplies several components or raw materials to you. If they're going to send a truck or a consignment to you, by looking at the buffer status of the items they supply, it's possible to make up a consignment based on those items with net flow in the yellow zone and their replenishment quantities. If there's still space on the truck and one wants to make up a full truckload, then some items where the net flow is close to the bottom of the green zone could be included in the consignment. A similar situation might arise when you're sending a truck to a distribution center. The first items to be loaded would be those with net flow in the yellow zone based on buffer status, and again filling any extra space up on the truck with items with a net flow close to the bottom of the green zone. Occasionally, we might want to deploy all the stock at the sourcing unit out to the distribution centers. In this case, there are two scenarios. We might have more than is required to top buffers up as far as net flow is concerned to the top of green, or the reverse could be true in that there isn't sufficient to top up every buffer to the top of green as far as net flow is concerned. In both these cases, the system will deploy stock to the distribution buffers in a prioritized share, such that all buffers for the SKU will be at a similar percentage, either below or above the top of green after deployment. This concludes this podcast on demand-driven planning. However, the Demand-Driven Planner course goes into this subject in a lot more depth and detail. Next time, we will examine the fifth component of DDMRP, which is visible collaboration and execution. Remember also that the third edition of Carol and Chad's book, Demand-Driven MLP, also gives you a more in-depth look into these podcast subjects. So until next time, continue your research into this very important supply chain subject of demand-driven MLP. I'm Ken Titmus, and you can contact me at ktitmus, that's KTITMUSS @mweb.co.za, or go to the DDI website at www.demanddriveninstitute, or one word, .com.